is that the initial value A0 is also called, it's called the initial value, so it's also called the seed value. For the sequence. Yeah.
So isn't, like, I don't want to like jump ahead, but isn't basic cryptography when you take a message, you put a prime number at the end and then multiply it by another prime number?
Maybe. There's going to be some prime numbers though, that's for sure. Prime numbers are super useful for the seed value. Now, so the way we're doing it is this, like we've done so far, is to take a message, get a sequence of numbers, and add them to the message to make noise, so that it gets obscured by the noise sequence. So the most secure one is to make a random sequence by just rolling a dice or something, and add that to your message. And it's totally uncrackable because it's a completely random sequence. You have to have the whole sequence to decrypt it. But a lot of times instead, use a sequence with a formula that looks random. Yeah, question.
Is this in chapter 5?
Yeah, still chapter 5. Mm-hmm. Yeah. So we're still in chapter 5. Chapter 5 has the recursive sequences, the inductive proofs, and then the application of them is the cryptography. Mm-hmm. Okay, so here's where the prime numbers come in. If you know the formula and the seed value, you can decrypt or encrypt, both. Like we've been doing. You got to know the formula for the sequence and the seed value for the sequence. Then you can create the sequence and decrypt it or encrypt it. And we'll do that for an example real soon, so in case you haven't seen it enough. More is coming. So here's what RSA, those guys invented, is the prime number idea. So first of all, I'll do the simplest one, which is public key encryption. They have a secret key. The A0 is a secret seed value, but you choose A0 as a large prime number. Then you pick another second large prime number. So call the second one just X or something. And you publicly publish the two numbers multiplied together. So you could call that so A0 times X. Maybe just call it M. So for the RSA sequences, the important thing is that you can use A0, or you need A0 to encrypt it. But you can, well, you need it to find A sub n and encrypt, like we've been doing. But you can decrypt with that product, with M is equal to A0 times X. All right, well, so the cool thing about that is then they can publish the key. That's the public key part of it. And they give you that on, you know, like on the website. And by they, I mean your bank. So your bank is using RSA. So the bank can send you, so your bank, say, can, number one, encrypt your private info or your statement. With A0 to publish M, which is the A0 times X. And then you can decrypt your statement. So it comes to your phone, and your phone decrypts it for you and tells you how much money you have in the bank. And the important thing is, nobody else can send you a fake statement with this, because nobody else knows A0. Only the bank knows A0. The bank keeps A0 secret. So what it does is it makes a secure signature. The bank itself is the only one that can send you your statement. Just as an example, that might not be really secret info or anything, but no one else can. Well, probably a better example might be going the other direction, where you can encrypt a payment and send it to them, but no one else can decrypt the payment except them. I think that was even better. Or so. So the prime numbers, which we should review what those are the ones that only have divisors of 1 and themselves. And when you have a product of really big prime numbers, the only reason this all works is that there's no known way to quickly factor and figure out what A0 is. So it only works since there is no known factoring algorithm that can quickly take M and figure out A0. Which is kind of surprising. Factoring is something that everybody does really early on in elementary school. You know, you take a number like 35 and you figure out that it's 7 times 5. But, or an even number like 30 and it's 3 times 10, but that's 3 times 2 times 5. So you find all the prime numbers that factor it. But that's only, you can do that with small numbers, but as soon as they get big, it takes way too long. So here's recall the prime numbers just in case. So it's P, typically just positive. We don't worry about negative numbers. And they're all the ones such that, well, 1 always divides P, and P always divides P. And also negative 1, so plus or minus 1 divides P, plus or minus P divides P, but no other integer divides P. Now, by that definition, the number 1 is a prime number since it divides itself. And people don't know whether to keep 1 or not. That's just a matter of style. So I'll put in parentheses. 1 works, 2 works. There's only 1 in itself going to 2. And then 3, 5, 7. Now it looks like it's all the odds in 2. But of course 9 you have to skip because 3 divides 9. So skip to 11. 13 is okay. 15, 5 is 5 times 3, so you skip 15. 17 is 1. 19 is 1. 21 is not prime because it's 7 times 3. But 23 is. Of course 25 is not. 27 is not because it's 9 times 3. But 29 is. And 31 is, and these go forever. So actually the proof that there's an infinite number of them is a pretty easy proof to do with contradiction. Assume that there isn't an infinite number, and you can always find one more. But I want to get back to the encryption, so I won't prove anything about prime numbers for right now. It's easy to go on a nice bunch of rabbit trails with these though, because there's so many unanswered questions like so there's a lot of prime numbers where there's 2 in a row, like 17 and 19, or 29 and 31, where there's just a difference of 2. You just add 2 to them. So those are called twin primes. And there's, nobody knows if that keeps going forever. Like, can you always find an infinite number of pairs? It's conjectured that there are. As far as we know, we keep on looking further and further out. But nobody's been able to prove it. Oh, an even easier one is that if you take any even number, it's not in that list except for 2, but take any even number at all, as far as we know, you can always turn it into a sum of exactly 2 prime numbers. So like if you took 30, 30 is equal to 13 plus 17. Yeah. Or if you take like 50, 50 is equal to 25 plus 25, but those aren't prime. So keep looking on both sides, and when you get to like 29 plus 11, does that give you 50? No, that gives you 40. They have to go up a little bit bigger then, maybe. I don't know if I can see the pair of numbers on here that go up to, that do 50.
19 and 31.
19 and 31 give you 50? Yep. Yeah. That's called, the guy that invented it, or thought of it, the Goldbach conjecture. So like 50 equals 19 plus 31. Any even is the sum of two primes. We don't know. Just like we don't know if there's an infinite number of twin pairs. So I think there's some prize money you can get by solving one of those, but lots of people have tried to come up with a proof, but never found it. It's very tempting. But then this one, there's another unknown. If you have two big prime numbers, the only way we know how to factor them is basically, there's some tweaks, but basically the long way is to go through a whole list and try it and do long division as you go. You know, does 29 go into it? Try the long division. Does 31 go into it? Try the long division. And so if you know this public key M, if it's big enough, just make it into trillions or something, then the long division takes way too long. Each attempt takes too long to try, and they add up to being longer than thousands of years. Basically, it would be worthless to crack it by that point. It wouldn't be any use anymore. So maybe even just the life of the universe or something takes that long. So if somebody invented a fast factoring algorithm, though, there's no reason to think it doesn't exist. No one's proven that there's no fast factoring algorithm. We just don't know it. So a ton of the encryption that we rely on is founded on the fact that nobody knows a fast factoring algorithm. And if someone ever finds it, they'll be able to hopefully be honest and tell everybody else so that we stop. But
wait, so how is -1 a factor of p if it's all integers greater than 0?
Oh yeah, the p is the number that's greater than 0, but you can always do like -1 times -p equals p, right? So most people just leave that off and say 1 and p are the only positive factors, but it's true that if you're going to use the division symbol, the negative does divide it as well. Right. Wow. So here's an example. So all this about the big prime numbers multiplied together is kind of just for your information, because I don't think we'll have time in this class to really do an example of that. It's more like a computer project. So if you take a cybersecurity class, you'll probably end up getting to do that on a computer with some big prime numbers. But we can do the blum blub shove algorithm. It's just another example of the same stuff that we've been doing. So here's the BBS sequence. It looks like this. A sub n is equal to a sub n minus 1 squared, and then mod p times q. A sub 0 is given. Okay. It's got some variables in it. So if I ever give you this one, I have to tell you what the variables are. P and Q are given prime numbers. And A0 is a given seed, A sub 0. Seed value. And to make it a real Blum-Blum-Shub sequence, the A0 is no good if it's 0 or 1, or if it's divisible by P or Q. So A0 is not equal to 0 or 1, and you want P does not divide A0, and Q does not divide A0. So, but all of that, just more historical interest, because if I give you an example of it, I'll have to tell you those numbers. So here's an example of a problem that we'd actually do. Like I would say, use the Blum-Blum-Shub sequence to...
Wait, how are there infinite twin pairs with the twin primes?
Oh, for that one, it's, I don't know, you can kind of believe that maybe it would be false, that there aren't. Nobody knows. But they're always finding new ones. They're further and further apart. Like at first, they're all twin, like 3, 5, and 5, 7. But then they start skipping. So the 17, 19, and 29, 31 are not next to each other. But then if you go out further and further, you still find more. Like I don't know, a trillion and 1 and a trillion and 3. But I don't think those would be likely. They're pairs that are both prime, but only 2 numbers apart. They get harder and harder to find, but the conjecture is that you will be able to find an infinite number of them. Keep going, you'll always find more. So, here's an example. Encrypt hello using the BBS sequence with, and I have to give you these numbers, P equals 5, Q equals 7, and A0. So for the seed, for a real seed, we want some sort of really big prime number, right? But that's not great unless you're doing it on a computer or a calculator or a spreadsheet or something. So I'm going to have to pick a small number, and it won't be the best encryption ever. All I have to do is make sure it's not 0 and 1. If you pick 0 and 1, it turns into a boring sequence because it just gets 1, 1, 1, 1. But I want also just something that P and Q don't go into. So I can pick a number that won't work out very well, but it'll be fine for example. Okay, so for the example, you'll have that problem. Okay, so the sequence then, first thing to do is find the sequence. And it would be 0, 1, 2, 3. I'll need 5 terms to do hello. So A0 is given. That one's given. And then the formula is to square it and mod it by PQ. So P times Q is 35. I'll just put that in parentheses. So for A sub 1, you're supposed to take the previous, which is 8, and square it and mod by 35. So that'll be 64 mod 35. So it's going to take, this one, I may have picked a number that's even too big for working by hand. That's not too bad. 35 goes into 64 once, and The remainder will be whatever 64 minus 35 is. So I have 5, 14 minus 5, 9, 29. So that equals 29. The real calculation is that 35 goes into 64 once, and then that's 35. You get 29, and the remainder is 29. So didn't need to do all that there. Yeah. So a little scratch work for that one. And then a sub 2. I take the previous answer, so I got 8, and then 29, and I square it. 29 squared mod 35. Alright, this turned into a bit of a calculator problem. I had to work it out already, so I did. 29 squared is, so you get like 20 times 20 is 400, but then you have the 20 times 9 and 20 times 9. I think it turns into 841. Which means long division time. Here's another scratch work. 35 into 841. Alright, so into 84 twice because that's 70. It's been a long time since I've done this. And then 141. Subtracting the 700. It's really times 20 because you're in the tens place here. So it's minus 700. It's weird to bring down the 1 like that, but it's really just minus 700. That's how you usually write it though. Well, 70 times 2 is 140. So 35 times 4 is 140. Yep, I wouldn't make you do that big of a problem on the test. So 1. So remainder is 1. So the answer here is a 1. Oh, so this shows me why 8 was not the best seed to use, because now look what happens. Next thing I do is square 1. So 8 sub 3 is equal to 1 squared mod 35 equals 1. Because 1 squared is 1, mod 35. 35 goes in 0 time, remainder 1. And the last one will have the same number. A sub 4 will be equal to 1 squared mod 35 equals 1. So if you don't pick a good seed, pretty soon you just get 1s, which will be pretty bad for encryption. But I had to pick something small enough so that I could do it on the board. That was almost too big. You get more interesting numbers if you pick a bigger A0, because then it'll start out squaring pretty large, and you might get some interesting numbers going down. But so that's our sequence: 8, 29, 1, 1, 1. And then to encrypt hello with it, it's the same process that we've been doing. So any question on those? All right. So the encryption would be, here's the message, was HELLO. And I like to provide the grid for you on the quiz. When I pass it out on Friday, I'll draw it for you. Then turn it into the standard letters. Oh, I also provide that on the quiz, but you have them in your notes from the last several days, right? I'll need to write them on the board again. H was 8, E is 5, which that one you memorized pretty fast since E is the most common. L is 12, 12, O is 15. So those are the standard numbers. And then you add on the sequence. So the sequence is 8, 29, 111. At least that'll make it easier when I get to that part of the encryption. Then you add the mod 26. So So 8 plus 8 is 16. Mod 26 equals 16. 29 plus 5 is 34. Mod 26. So let's see. Yeah, I'll leave a long stretch here for you if you want to do calculations in there. 34 mod 26. So 26 does go into 34 once, and then the remainder would be 8. Yeah. 12 plus 1 though, now these are going to be easy. So 13 mod 26 is 13. 13 mod 26 is 13. Whenever you have a number that's smaller than 26, it's itself. 16 mod 26 equals 16, because that's the remainder. 16 goes into 26 0 times, remainder 16. And then back to letters again, right? So let's see. The letters are from the chart. P and H. 13 was M and another P. So that's the encrypted message is PHMMP. And then to decrypt it, with this method, you'd have the same sequence, but subtracted mod 26 each time. Well, mostly historical interest, because it's just another sequence that you can use. That I would have to tell you the sequence itself for you to be able to find the answers. I could make you memorize this formula here, but I probably won't. I'll just go ahead and give you the formula. So in the question, I'd say, remember, the BBS sequence is a sub n equals a sub n minus 1 squared mod PQ. And then I would give you PQ and A0. If you're going to do that one. It's more interesting on a computer, though, because then you can give it giant numbers and see all kinds of random numbers coming out, making it a decent encryption. All right, so next is something much easier. It's much easier to encrypt if you're working just with binary. But we need to do it so that you know what it looks like. So this will be encryption of binary messages. So first of all, a binary message is sort of already encoded, but it's a well-known standard code, like using the ASCII codes for letters, and using the ASCII codes for letters, but then translating them into binary. So using the machine language for letters or something. So it's already, the message itself is already in standardized binary code, like ASCII. But we don't want to keep that because everybody knows that's standardized. Just like we don't want to keep the numbers 1 through 26 as our secret code for the letters A through Z. So, let's finish that parentheses. We do the same thing. We add some sequence a sub n to the message. So it'll be another sequence, and any sequence that you want. It could be a one-time pad that I give you, or a formula where you calculate the terms in the sequence. And this time, though, you don't add mod 26, right? You add mod 2. Because in binary, there's only two letters in the alphabet. Yeah, they're not really letters, so I'll put quotes on them. They're the two symbols, 1 and 0. So the process will look the same like this chart, except the first line will be a message that I have to give you, and it'll just be 1s and 0s. Then you don't have to write the standard numbers because it's already standardized. We can learn how to turn a letter message into ASCII code and then into binary, but I don't have that memorized. It's out there somewhere. We can look that up if we wanted to. But for this, I'll just give you the message with 1s and 0s, and then I'll give you the sequence, and then you just have to add them together, mod 2. So adding mod 2 is the only new thing here, and it's not very hard. It's actually, it's so easy that it's easy to get confused. I don't want to do it too fast, in other words. Like, it's so easy that I could just do it in my head and no one would know where I was getting the answers, right? It turns out mod 2 is the same thing as asking if 2 goes into it or not, because the remainder is either going to be 1 or 0. So let me write a couple of those things down. So note, so if you have some number z mod 2 will be the remainder when dividing by 2. So it'll equal 1 or 0. Yeah, it's pretty obvious. Which is same, also obvious because when you add mod 2, you're just going around the circle again. It's a very small circle with just 2 things on it. Okay, example then. So encrypt the message 1101 using the, let's see, what sequence should I use? Oh, I better not take up too much time. It's using the one-time pad. And the one-time pad is n equals 0, 1, 2, 3. A sub n is 4 random numbers, which I'm getting from mental dice. 3, 11, 14, 7. Okay, so here's the answer then, is to make another chart where you have the message on one side, which is 1101. Then the sequence, which I just gave you, A sub n, which is 3, 11, 14, 7. Then you add it on in mod 2. So first I'll get 3 plus 1 mod 2, which is 4 mod 2. And the remainder, when you put a 2 into 4, is a 0. So now it's tempting to go fast. You can tell when you add them together, it's pretty easy to see whether the remainder is a 0 or a 1. if it turns out to be an even number when you add it, you it's going to be remainder 0. But I'll show some more work. 1 plus 11 mod 2 is equal to 12 mod 2 equals 0 because the remainder is 0. Oh no, they're all going to be 0, aren't they? Hey, that's a great code. The message looks like it's just an empty channel sending zeros. So I'll go ahead and do the addition. 14 mod 2 is equal to 0, and 8 mod 2 equals 0. So that's the answer. The answer is already in standard form. 0, 0, 0, 0. You don't have to look back at a chart and turn it into letters because we're working with binary messages anyways. So the answer is 0, 0, 0, 0. Definitely need some more examples, and so to make sure they come out with not just zeros every time. They don't, because and then it's interesting to see how a circuit would do that too, since we know how to do things with binary on circuits. Yeah, question.
Encryption on the next quiz, you look for it to spell an actual word, so that way we know if it's just nonsense.
Oh yeah, right. So nice thing about it with letters is if I say decrypt this message, I should say it makes a real word to help you out a little bit. And with binary, you know, it's just going to be a random string of 1s and 0s, so you just have to be careful. Yeah. Yep, okay. That's it for now. If anybody had a